Okay, I think we'll get started. So today we're going to introduce the equilibrium constant and the reaction quotient. And we've been talking about species in solution, and we've talked about concentration. So we're building up to the point where we can actually have a chemical reaction happening in the beaker. And so the next several lectures, many of them, will be developing these ideas associated with chemical reactions. And so this is really the heart and soul of what would be considered a General Chemistry 2 course, and it's certainly the heart and soul for chemical equilibrium. So we're laying down some foundations now for the next few lectures. All right, so let's consider just a very generic reaction. A moles of A plus B moles of B go to C moles of C and D moles of D. Then we know that some reactions go quite a ways, almost completely to products. Some reactions barely go at all, and many reactions are sort of halfway in between. But in all circumstances, reactions will come to some sort of equilibrium. And that may be very product favored, might be very reactant favored, or it might be a mix somewhere in between. But that will happen, and that's called a chemical equilibrium. And a chemical equilibrium is a dynamic equilibrium. So it isn't that the reaction stops, the forward reaction keeps going, the backwards reaction keeps going, but it's going at an equal rate so that the reaction, the net reaction, there's no observable net change in the reactants or the products. All right, so among the questions that we're going to ask, we're going to hold off on the question of how fast this reaction gets to equilibrium. That's a whole different area of chemistry called kinetics. We'll hit that towards the end of this Introduction to Physical Chemistry 2 course. But now we're just worried about the reactant state and the product state. And so when we talk about that, we're comparing the reactants sort of as one state of the system, and then the products as the other state of the system. We're comparing reactants to products, and that will help decide where this equilibrium will lie. And so some of the questions that we'll ask is how much of A, B, and C and D are left after the reaction has got to equilibrium? How much energy is evolved? If we disturb the system, how does that change? So lots of questions will come up here. All right, so we'll start with just defining what's called the equilibrium constant. So we'll stop short today, and at least for a little while, on getting the actual values for these, but we can say something about the ratio. And it's a complicated ratio here, but it's products over reactants. And so there's this mantra in chemical equilidynamics, products over reactants. What does that really mean? It means the products raised to their stoichiometric factor, whatever that reaction may be. So this equilibrium constant is associated with a reaction, and we raise the concentrations of C and D to their respective powers here, and then we divide by A and B concentration raised to their respective powers. Now, we haven't talked about gases yet. That'll come towards the end of the course, but we can still think about reactions that happen among gases, and we don't have to get into more careful study of gases. So if we've got a container and there's a certain amount of A, B, C, and D in that container, instead of concentrations, although we could use concentrations, what's usually done in a gas phase reaction is to use something called the partial pressure. Then we have a Kp, which is very much related to the K here, and that's the partial pressure of each of these. And what that means is if we've got this vessel, it's got a certain total pressure. How much of that pressure is due to the fact that molecules or species C is present, species D, and so on. So this is the component of the total pressure that each of these species make up. And so for gas phase reactions, we often work with a Kp. So as you start working problems in your chemistry book, whatever book you have, they'll give you a lot of examples with K and with Kp. All right, a couple of other things that I'm just going to tell you for now. When we have a reaction, say something like this, so aqueous, 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 and then we form water, let's say. When we write the equilibrium constant, we'll take the concentration of the products, concentration of the reactants, but water is sitting here. This is really a 1 that's sitting there, and we don't quite know why yet, but this is not given to us. We don't use the concentration of water here. And in fact, this is true more generally. If we create something that comes out of the solution, like a gas or a solid, then that would be sitting here as just a 1. And so for now, just sort of take that. Most of this course, you'll just have to kind of take that as information. And later in the curriculum, we'll learn more why that is. It has to do with our choice of reference state for each of these different species. All right, well, that's our equilibrium constant. Now, what about just taking the ratios in that way at any course of the reaction? So not necessarily at equilibrium. So like from right when we dump the solutions together to maybe all the way to equilibrium. And then even though we wouldn't see this happen on the bench, we could imagine pushing that reaction past equilibrium such that if we stop doing that, it would want to come back. So you want to think of the chemical reaction as all the way from reactants all the way to products, and the system will naturally come to equilibrium. If we're too far to products, then we'll come back to equilibrium. If we're too far to reactants, we'll come to equilibrium. So we want to be able to describe where we are in the reaction at any given situation. And so we write the analogous ratio, but we can't call it an equilibrium constant. We can't even call it constant. So this is a constant. This will be what these are when we come to equilibrium. That won't be changing. That'll be a constant for a given reaction. But this will depend very much on where we are in that range of possible states. And so this is called the reaction quotient. And easy to get this confused with K. So always remind yourself, are we at equilibrium? Are we out of equilibrium? Then, of course, at equilibrium, Q equals K. And then Q gives us a good sense of where we are then in this reaction. Since we have our products on top and our reactants on the bottom, if our Q is greater than K, that means the numerator is bigger than it should be, or the denominator is smaller than it should be to be at equilibrium, in which case we've got too much products relative to reactants, and so our reaction will go backwards. So if we have a K value, we have a Q value, and if Q is greater than K, then we're on the other side of equilibrium. We're going to come back this way. Likewise, if Q is less than K, then we're not yet to equilibrium, and we will still continue to move forward. All right, now associated with this is a very important principle, and actually we're going to really hammer this principle. This is the first time we'll see it. This will be in a very qualitative way, so we won't talk about calculating anything here. But then later, after we've done some things with reactions, we come back to talking about things more generally. We'll come back to this idea and give it a quantitative nature. And this idea is called Le Chatelier's principle. And the idea here is if a system is in equilibrium, so we let our system come to equilibrium, we've got whatever amount of reactants and products are there that are supposed to be there for equilibrium, then we disturb that equilibrium. So what does that mean? We might pull out a little reactant, or we might add a little product, or we might change the temperature, or if it's a gas phase reaction, we might change the pressure. We do something to disturb the equilibrium. And Le Chatelier's principle says, then the system will act to reestablish the equilibrium. So what does that mean? If we've got, use blue here, if we've got, say, A plus B goes to C, let's write the equilibrium constant for that. Now, let's say we make some kind of disturbance. So let's say we're trying to pull out product. This is some important drug to save the world or something like that. And so we pull the product out of reactants. So we're gonna make a disturbance by dropping C. Well, what happens here then is when we pulled the C out, we have lowered the concentration that it should be to be in equilibrium. And so we're out of equilibrium, and that Q has a new C. And the new C is less than the one at equilibrium. So that means Q is less than K. And when Q is less than K, our reaction should go forward. So we've removed product. The system wants to reestablish that. So the reaction goes to make more product. It's just compensating for what's happening. Likewise, we could have, say, removed reactant. So let's take A down. Then K. Right, we're going to remove A. We're going to make A less. That means the new Q is going to be greater than K. And our reaction will go backwards. And so thinking about this just intuitively, once we internalize this idea of reestablishing the equilibrium, if we're going to remove some A, then our reaction has to go backwards in order to compensate for that or recorrect for that. Okay. All right. So at this stage of the game, and this is where your general chemistry book this is all your general chemistry book will do, is have you think about this idea, sort of develop that chemist's intuition about how things should go and not do any kind of algebra or calculations there, other than maybe quickly thinking about how Q is related to K after the disturbance. We will go through a very nice algorithm for determining which way the reaction will go and actually be able to put some numbers to that and calculate things that would happen if we, say, cut the product in half or something like that. But that'll come down the line a little bit. All right, the last thing we want to talk about is exothermic and endothermic reactions. An exothermic reaction is a reaction that gives off heat. So if you mix A and B and it creates C, the reaction gets hot. If you were to touch the beaker, it would feel hot. It's giving off heat. The endothermic reaction, takes in heat. So if you mix these two and then touch the beaker, it would feel cold. So some of those cooling packs where you pop them and mix them together and then they get cold, that's an endothermic reaction. So it's getting colder, it's pulling heat from your body then, and you're using it as a ice, essentially an ice pack. Exothermic, maybe hand warmers. If you live far enough in the north where you've maybe had some hand warmers, you crack them open, mix them a little bit, stick them in your mittens, and they'll produce warmth. That's an exothermic reaction. Heat is given off. So how can we connect this to Le Chatelier's principle? Well, we write a little delta here to represent heat. And if it's exothermic, so this is an abusive notation. So it isn't something that we can really do rigorously. But we'll say, let's just put heat as if it were a reactant or a product. If it was a reactant, then it's taking heat in. That's endothermic. If it's a product, it's giving heat off or it's producing heat. That's exothermic. And then we can talk about a disturbance of temperature. So we've come to equilibrium, we cool the reaction. If we cool the reaction, then that's like removing heat. So if we're in this case and we remove heat, then we will shift in this direction. If we're in this case and we remove heat, we will shift back in that direction. So we can treat it as if it were a product or a reactant when we're thinking about Le Chatelier's principle. And we're mixing a lot of things here. We're kind of thinking of temperature as heat, which of course it isn't. But it's a way that works with our intuition. Now we will again make this more rigorous after a few lectures, and we'll actually see what really happens when we reduce the temperature, and we'll get an idea that we'll get the results that are consistent with this picture. All right. So your book will have a lot of homework on this type of thing. It's the first part of stuff that'll quickly get harder, so we're going to progress into that. But work through those first problems in your book. Think about Le Chatelier's principle. There'll be probably some conceptual questions in your book dealing with Le Chatelier's principle. This is a good foundation now as we start talking about chemical reactions and reaction equilibrium.